Arranging switchgears back-to-back offers several advantages. Firstly, it provides space savings, which is especially beneficial in locations where area is limited. Secondly, improved access is achieved when draw-out breakers are on the front because it simplifies maintenance and troubleshooting. Thirdly, reduced cable length is a benefit, as connecting switchgears back-to-back shortens the distance between them, leading to savings in materials and labor. When draw-out breakers are located on the front of the switchgear, some wiring from the back may be necessary to interconnect them. This wiring encompasses several types. Firstly, bus connections. The buses connecting the switchgears need to be wired from the back. Secondly, control wiring may be required to enable remote operation of the switchgears. Thirdly, auxiliary wiring might be needed to connect additional components like sensors or relays. Working on back-to-back switchgears necessitates strict adherence to safety precautions. Firstly, always implement lockout/tag-out procedures before commencing any work on the switchgears to de-energize the equipment. Secondly, wear appropriate personal protective equipment, including gloves and safety glasses. Thirdly, maintain awareness of the surrounding environment, particularly the location of live wires and other potential hazards. Also, strictly adhere to the manufacturer's instructions for installation and maintenance procedures. Space optimization is a key reason to arrange switchgear in a back-to-back configuration. This is especially helpful in areas where square footage is at a premium. In dense urban environments or industrial facilities with limited space, a back-to-back arrangement can significantly reduce the overall footprint of the electrical equipment. The arrangement allows for a more compact layout, freeing up valuable space for other purposes. Improved accessibility is another significant benefit. The design with draw-out breakers located on the front of the switchgear makes maintenance and troubleshooting operations more accessible. Technicians can easily access the breakers from the front, simplifying inspections, testing, and component replacements. This can lead to reduced downtime and faster maintenance cycles. Reducing cable length is an economic advantage. By placing switchgears back-to-back, the distance between them is minimized, thus reducing the required cable length for interconnections. This leads to cost savings on materials and labor, as shorter cables are less expensive and require less time to install. Over the long term, these savings can be substantial, especially in large-scale installations. The wiring from the back typically involves three primary types of connections. Firstly, bus connections, which are essential for transferring power between switchgear sections. Secondly, control wiring, which facilitates remote operation and monitoring of the switchgear. Thirdly, auxiliary wiring, which supports additional functions and components. Each of these wiring types plays a crucial role in the overall functionality and reliability of the system. Bus connections are the backbone of the power distribution system within the switchgear setup. They provide the main pathway for electrical current to flow between different sections of the switchgear. These connections are typically made using copper or aluminum busbars, which are chosen for their high conductivity and ability to handle large currents. Proper installation and secure connections of the busbars are critical for ensuring a reliable and safe power distribution system. Control wiring is used to remotely operate and monitor the switchgear. This includes functions such as opening and closing breakers, adjusting settings, and monitoring system parameters. Control wiring enables operators to manage the switchgear from a central control room, improving efficiency and response times. These circuits often involve low voltage signals and require careful routing and termination to prevent interference and ensure reliable operation. Auxiliary wiring supports a variety of additional functions and components within the switchgear. This may include connections to sensors, relays, meters, and other devices that provide critical data and control signals. Auxiliary wiring allows for enhanced monitoring and protection capabilities, improving the overall performance and safety of the system. Proper identification and labeling of auxiliary wiring are essential for simplifying troubleshooting and maintenance. Safety is paramount when working with switchgear, and several precautions must be taken to protect personnel and equipment. Firstly, lockout/tag-out procedures should always be followed to de-energize the equipment before any work is performed. Secondly, appropriate personal protective equipment (PPE) must be worn to protect against electrical hazards. Thirdly, awareness of the surroundings is crucial to avoid contact with live wires and other potential hazards. Always following the manufacturer's instructions is essential for safe and proper installation and maintenance. Lockout/tagout loader is a safety procedure used to ensure that dangerous machines or equipment are properly shut off and not able to be started up again prior to the completion of maintenance or service work. It requires that hazardous energy sources be isolated and rendered inoperative before any employee performs service or maintenance on the equipment. This procedure involves placing a lock and a tag on the energy isolating device to prevent accidental energization. Personal protective equipment (PPE) includes items such as gloves, safety glasses, hard hats, and arc flash suits. The specific PPE required will depend on the type of work being performed and the potential hazards involved. It is important to regularly inspect PPE to ensure that it is in good condition and provides adequate protection. Maintaining awareness of the surroundings involves being vigilant about potential hazards such as live wires, exposed conductors, and moving parts. It also includes being aware of other workers in the area and avoiding distractions that could lead to accident. Regular safety training and adherence to established safety protocols are essential for creating a safe working environment. The manufacturer's instructions provide detailed information on the proper installation, operation, and maintenance of the switchgear. These instructions should be carefully followed to ensure that the equipment is installed correctly and operates safely. Deviations from the manufacturer's instructions can lead to equipment damage, safety hazards, and voiding of warranties. Proper planning is essential for a successful back-to-back switchgear installation. Firstly, conduct a thorough site assessment to identify potential challenges and ensure adequate space. Secondly, develop a detailed installation plan that outlines the sequence of steps and assigns responsibilities. Thirdly, coordinate with all stakeholders, including electricians, engineers, and facility managers, to ensure a smooth and efficient installation process. Regular inspections are critical for maintaining the reliability and safety of back-to-back switchgear installations. Firstly, perform routine visual inspections to identify any signs of damage, corrosion, or loose connections. Secondly, conduct periodic electrical testing to verify the performance of breakers, relays, and other components. Thirdly, maintain accurate records of all inspections and tests to track the condition of the equipment over time. Proper ventilation is essential for preventing overheating and ensuring the long-term reliability of switchgear. Firstly, ensure that the switchgear room has adequate ventilation to dissipate heat generated by the equipment. Secondly, monitor the temperature within the switchgear room to identify potential overheating issues. Thirdly, implement cooling measures such as fans or air conditioners if necessary to maintain optimal operating temperatures. Proper labeling is essential for identifying components and circuits within the switchgear. Firstly, use clear and durable labels to identify breakers, switches, terminals, and other components. Secondly, create a detailed wiring diagram that accurately reflects the connections within the switchgear. Thirdly, maintain up-to-date labeling and diagrams to facilitate troubleshooting and maintenance. Surge protection is essential for protecting switchgear from voltage transients caused by lightning strikes or switching events. Firstly, install surge protective devices (SPD) at the incoming power supply to divert surge currents away from the equipment. Secondly, coordinate SPD with other protective devices to ensure a comprehensive surge protection strategy. Thirdly, regularly inspect and test SPD to verify their performance. Grounding is essential for providing a low impedance path for fault currents and protecting personnel from electric shock. Firstly, ensure that the switchgear is properly grounded to a central grounding electrode system. Secondly, verify the integrity of the grounding connections using a ground resistance tester. Thirdly, regularly inspect and maintain the grounding system to ensure its effectiveness. Infrared thermography is a valuable tool for detecting hot spots and potential problems within switchgear. Firstly, use an infrared camera to scan the switchgear for areas of elevated temperature. Secondly, analyze the thermal images to identify potential problems such as loose connections, overloaded components, or insulation breakdown. Thirdly, schedule maintenance to address any identified issues before they lead to equipment failure. Arc flash studies are essential for assessing the potential hazards associated with arc flash events. Firstly, conduct an arc flash study to determine the incident energy levels at various points within the switchgear. Secondly, use the results of the arc flash study to select appropriate PPE and establish safe working distances. Thirdly, regularly update the arc flash study to reflect any changes in the electrical system. Power quality monitoring is essential for identifying and addressing power quality problems such as voltage sags, swells, and harmonics. Firstly, install power quality monitors at the incoming power supply and at critical loads. Secondly, analyze the data collected by the power quality monitors to identify potential problems. Thirdly, implement mitigation measures such as filters, surge suppressors, or voltage regulators to improve power quality. A well-documented maintenance program is crucial for ensuring the long-term reliability and safety of switchgear. Firstly, develop a comprehensive maintenance plan that includes routine inspections, testing, and component replacements. Secondly, maintain accurate records of all maintenance activities. Thirdly, regularly review and update the maintenance plan to reflect any changes in the electrical system or operating conditions. Retrofitting existing switchgear can extend its lifespan and improve its performance. Firstly, assess the condition of the existing switchgear to identify potential upgrades. Secondly, consider retrofitting with new breakers, relays, or other components. Thirdly, ensure that the retrofit is performed by qualified personnel and that all applicable safety standards are followed. Proper disposal of old switchgear is essential for protecting the environment and complying with regulations. Firstly, follow all applicable regulations for the disposal of electrical equipment. Secondly, recycle or dispose of components such as oil-filled breakers and transformers in an environmentally responsible manner. Thirdly, document the disposal process to ensure compliance. Continuous training is essential for ensuring that personnel are qualified to work on switchgear safely and effectively. Firstly, provide regular training on topics such as safety procedures, maintenance techniques, and troubleshooting methods. Secondly, ensure that personnel are certified or licensed as required by local regulations. Thirdly, encourage personnel to stay up to date on the latest industry standards and best practices. Emergency preparedness is essential for responding to unexpected events such as power outages, equipment failures, or natural disasters. Firstly, develop an emergency response plan that outlines procedures for responding to various scenarios. Secondly, conduct regular drills to test the effectiveness of the emergency response plan. Thirdly, ensure that personnel are trained to respond to emergencies and that they have access to the necessary equipment and resources. Remote monitoring and diagnostics can improve the reliability and efficiency of switchgear operations. Firstly, install remote monitoring systems to track key parameters such as voltage, current, temperature, and breaker status. Secondly, use diagnostic tools to analyze data and identify potential problems. Thirdly, implement predictive maintenance strategies to address issues before they lead to equipment failure. Cybersecurity is an increasingly important consideration for switchgear, especially in networked environments. Firstly, implement cybersecurity measures to protect the switchgear from unauthorized access and cyber attacks. Secondly, regularly update software and firmware to address security vulnerabilities. Thirdly, train personnel on cybersecurity best practices. Commissioning is the process of verifying that switchgear is installed correctly and operates as intended. Firstly, perform thorough inspections and tests to verify that the switchgear meets all applicable standards and specifications. Secondly, document the commissioning process to provide a record of the equipment's performance. Thirdly, address any deficiencies identified during commissioning before placing the switchgear into service. Load studies are used to determine the electrical demand of a facility and to ensure that the switchgear is adequately sized to handle the load. Firstly, conduct a load study to determine the current and future electrical demand. Secondly, select switchgear that is rated to handle the calculated load. Thirdly, regularly update the load study to reflect any changes in the facility's electrical demand. Harmonic analysis is used to identify and mitigate harmonic currents in electrical systems. Firstly, conduct a harmonic analysis to determine the levels of harmonic currents in the system. Secondly, install harmonic filters to reduce the levels of harmonic currents. Thirdly, regularly monitor the system to ensure that the harmonic filters are functioning properly. Power factor correction is used to improve the efficiency of electrical systems by reducing the amount of reactive power. Firstly, calculate the power factor of the system. Secondly, install power factor correction capacitors to improve the power factor. Thirdly, regularly monitor the system to ensure that the power factor is within acceptable limits. Insulation testing is used to assess the condition of the insulation within switchgear. Firstly, perform insulation resistance tests to measure the resistance of the insulation. Secondly, perform dielectric withstand tests to verify the ability of the insulation to withstand high voltages. Thirdly, regularly test the insulation to identify potential problems before they lead to equipment failure. Contact resistance testing is used to measure the resistance of the contacts within breakers and switches. Firstly, perform contact resistance tests to measure the resistance of the contacts. Secondly, compare the results to the manufacturer's specifications to identify potential problems. Thirdly, regularly test the contacts to identify potential problems before they lead to equipment failure. Timing tests are used to verify the operating times of breakers and relays. Firstly, perform timing tests to measure the operating times of breakers and relays. Secondly, compare the results to the manufacturer's specifications to identify potential problems. Thirdly, regularly test the timing to identify potential problems before they lead to equipment failure. Partial discharge testing is used to detect insulation defects within switchgear. Firstly, perform partial discharge tests to detect insulation defects. Secondly, analyze the results to determine the severity of the defects. Thirdly, schedule maintenance to address any identified defects before they lead to equipment failure. Vibration analysis is used to detect mechanical problems within switchgear. Firstly, perform vibration analysis to detect mechanical problems. Secondly, analyze the results to determine the source of the vibration. Thirdly, schedule maintenance to address any identified problems before they lead to equipment failure.